resonance structures, right? Organic resonance structures. The whole idea behind resonance structure is that we're just showing how electrons could be in different places, which gives us the same atom, right? And the more resonance an atom has, or a compound rather, the more stable it is. You can think of it because the electrons are actually going to be delocalized over several different atoms, which will make it much more stable. So let's look at a couple structures and see if we could, do some resonance and see what resonance is really about. So if I look at some resonance of this structure, the first one, right? How can I think of moving some electrons, which still gives me the overall charge on the molecule, which is zero, right? So somehow I could represent this molecule in a different way, which gives me the same overall charge, right? Once you start doing resonance, and you're losing your charges, right? So if you have a molecule that's overall charge is zero and your resonance structure is a +1, that's not a resonance structure, right? You're changing the charge. That's not a different molecule. That's a different molecule. That's an ion now. So that being said, I'm looking at this and I'm saying, okay, well, can I, I could probably take one of these bonds here, right? And put it on this nitrogen here, right? And the whole idea being resonance, sigma bonds are not included in resonance. Only pi bonds, right, in your lone pairs, right? So I could redraw this molecule into H, right? Right, with now a double bond to that nitrogen, with the nitrogen having the lone pairs, right? Well, what does this carbon do? This carbon now will have a charge of, well, 4 minus 3 is +1, right? And this nitrogen now will have a charge of -1 because you have 1, 2, 3, 4, 5, 6. So 5 minus 6 will give you -1 charge. And opposite, again, will give you overall charge of 0. So this is actually a good resonance structure. Now, can we draw anything else? Certainly, I can't move this triple bond here because moving the triple bond here, right? Nitrogen, this carbon right here will pick up an extra bond, which will become minus. We can't move any, other bond. As you can see, we can't move any other bond. So moving a triple bond here will be a disaster. Moving a sigma bond here will be a disaster. All right, so that wouldn't work. So this will be the only good resonance structure of this molecule. It's a good second one. How about the second one? All right. Looking at something like this, anytime you have a minus sign on the outside of a ring, that means you have a lone pair to a carbon, right? You have a lone pair outside. So I'm thinking the first thing I could do with this is that I could put these lone pairs in, right, to form a bond, right? Once I form a bond here, now this carbon right here will be over bonded, right? It will have 5 bonds. So I could kick this bond up, this oxygen here, to give me a negative charge. So a good resonance structure for this, right? Alright. Form a double bond right here. Right. Right. Form a double bond. I'm gonna kick this oxygen lone pair up. Right. Which will give me a negative charge on the oxygen. And think of it as this now will be stable, right? Because again, you have a minus charge and you have a minus charge, right? So kicking in this lone pair right here stabilizes this section, giving an overall charge of 0, right? Because that carbon went to having 3. This carbon went from having 3 bonds and 1 lone pair to now 4 bonds, right? Which gives an overall charge of 0. Now, can we do any other resonance structures for this molecule? Probably not, right? Because, right, there's no other real reason. There's no other resonance structure for this molecule. As you could see, you can't move these electrons here, right? Because then you need something to move, and there is a double bond here, so you can't move single bonds. You see, so it's like a chain of reaction. When I put in this lone pair, I was able to move a pi bond or a double bond. Put in this lone pair here. What am I going to move here? Nothing. I can't move a single bond. I'm breaking a bond. So therefore, this will be the only good resonance structure of this molecule. Let's look at the last one. All right. How about this one? All right. Immediately, looking at this molecule, I could see a pattern here. I could put these lone pairs in, all right, which will form a double bond here. Flip this double bond here, yeah, which I could then flip this double bond here. Let's see what it gives us, all right. So now I have a double bond here, right? Sorry for my horrible drawing. I have a double bond here, I have a double bond here as the arrow pointed to, and I just flip this this bond here to a lone pair, right? So that will give the oxygen a minus charge, right? Everything else is stabilized because flipping these lone pairs in here gives this carbon, right? Give this carbon equal to this bond goes here, but this double bond is also here. This imaginary double bond is also here, so this satisfies everything. This is good because we moved this up here, so you can see it's a chain of reaction. Now, can we do anything else to, do some sort of, of a good resonance structure, right? So I would probably, I don't know, maybe, right? Let's look. How about putting this in here, right? So how about flinging these electrons in here and then flinging these out here? Would that make sense? Let's see, right? Let's see, because some molecules have really, more than one resonance structure. Some molecules even have 4, right? So looking at this, flinging these electrons in will give me a double bond here, right? Give me a double bond here, right? And just fling those outside, right? Fling these lone pairs outside, which now gives me a minus on this carbon, right? And it makes sense, right? Gives me a minus on this carbon right here because, again, it's a chain of reaction. I put this double bond to form a double bond here, but I kick these out right here, right? And that's definitely possible. So that gives me a negative charge. And again, you could see that all of my charges remain negative, as was the original structure. So again, resonance structures, more stable, right? The more structures you have, the more stable your molecule is. And you want to know that you're doing good resonance structures, right? Whenever the charges have to be equal, right? You can't, have a plus charge and then on another resonance structure you have a minus charge, right? That doesn't give you the original resonance structure. So again,